So welcome to our new fluid mechanics problem today. We are still talking today about the Stokes layer. If you look at my channel, there is another video on the Stokes layer, and in that video we derived the analytical solution, the laminar solution. So today we are analyzing the Stokes layer a bit more in detail, and we are looking at the dissipation, particularly so at the energy dissipation. So we're asking ourselves how much mechanical energy does the Stokes layer dissipate. So we're trying to answer this question. Okay, so to do that, we need to just remind ourselves what the Stokes layer is. So the Stokes layer is the fluid analyzed by Stokes and is also called the Stokes second problem. So it's a laminar, unsteady, viscous flow, and this flow is generated by a flat plate that oscillates in its own plane according to a sinusoidal law. So U at the wall, so at y equals 0, where y is the wall normal coordinate, as a function of time, is a certain u bar cosine of 2 pi t divided by big T, where t is the period and u bar is the maximum velocity. So we saw that the velocity profile is confined into an envelope, an exponential envelope. So when, for example, when the velocity is maximum on the wall, then the velocity profile will look like that. So each particle of the fluid at a certain location from the wall oscillates in planes that are parallel to the wall. And so we can write the solution in quite compact form. So u as a function of y and t, so we have the velocity in planes parallel to the wall, can be written as follows, as u bar, which is the maximum velocity at the wall, times the real part of E minus C 1 plus I y times EI omega t, where C is a constant we have defined, is the square root of omega divided by 2 nu, where nu is the kinematic viscosity of the fluid, and omega is 2 pi divided by big T, so is the frequency of the oscillation. So we know now exactly how the velocity behaves as a function of time and the distance from the wall. And what we want now, we want to analyze this fluid system under an energy point of view. So if this is the wall and this is the fluid here, then we can define a control volume and we imagine that this control volume is confined at the wall by a certain area AS. so the area of the surface that we consider for control volume, and we imagine that this control volume extends along the y direction at an infinite distance. Okay, so what's the energy balance that occurs in this flow? Well, we're certainly injecting some power, and we call this PSP. So P spent is the power used by an external agent to activate the surface, power used to move the wall. So what happens is that we need to expend energy to move the wall because we have to win the viscous resistance of the fluid. So then this power, PSP, must be equal to a certain D. And D is the dissipation into heat. So D, dissipation of power by viscous effects into heat. And then at each instant time, the power that we spend, we inject into the control volume from the wall. So part of it will be dissipated into heat, and part will contribute to the change of kinetic energy. So delta EK is the change of kinetic energy. So at each instant in time, the power spent is dissipated into heat and contributes to a change in kinetic energy. So let's look at these terms a bit more in detail, and then, so if you're interested in problem, you should refer to the book by Hinze, Turbulence, and also the classic by Batchelor, Introduction to Fluid Mechanics. To fluid, I think it's dynamics actually. So to classic text, and the first one is slightly more advanced, but you will see that the change in kinetic energy of a fluid, and in this case we have a fluid that has only, so the flow has only one velocity component, so the change in kinetic energy per unit time is delta EK is equal to rho partial T of U squared. Okay, so let's careful at the units here. We have kilograms meter cubed, so this is the density, and then we have 1/2 seconds, and then we have a velocity squared. Okay, so the units of this are kilogram divided by meter seconds cubed. So what we are interested into in this problem, we are interested in a time average. Time average of the Stokes layer. So if we time average this and we consider an incompressible flow, so rho is constant because we have d rho dt, where big D is the material derivative, equals 0. So in this case, if we average over time, we have a periodic flow, then we average over time. So for example, if we average over the period, actually be correct to say from 0 to t of rho times partial t u squared, then this is exactly equal 0, because we have that this is exactly equal to u squared at time t equal big T minus u squared at time t equals 0 multiplied by the density. And divided by time. But this is equal to 0 because the flow is periodic over a period. So there's no change in kinetic energy over a period of time. And so this is for each point in space. Actually, we have missed a 2 here. So divided by 2, 2, and here we have but it doesn't really matter because it's 0 anyway. Okay, so let's look now at the balance as a time averaged. So we already time averaged the change in kinetic energy, and we found this to be 0. So this means that we are left with a balance between the power spent, that's the power injected into the fluid, spent to move the wall against the viscous resistance, that must be equal to the dissipation. So if you look in the 2 texts that I suggested before, then you can find an expression for the dissipation of mechanical energy into heat. So I think the best is probably to look in Hinze, so 1975 edition. And so the dissipation, let's call it here phi, this is power, so watts per unit volume. So for a fluid, that's equal to mu, that's the dynamic viscosity, divided by 2 times partial ui partial xj plus partial u j partial xi squared. So where ij is follow the Einstein repeated index notation. Now, but if you remember, the velocity of the Stokes layer is this, so u just depends on y and t, so there's only u along the direction parallel to the wall, it just depends on y. So if we substitute that inside this expression, and we can find the dissipation, the power dissipated per unit volume. So for the Stokes layer, we have phi equal mu partial u partial y squared. And we note that the 2 has disappeared because we find two terms that are equal to this square root of the gradient. Okay, so let's write the velocity again. U bar E minus Cy, and then a real part of EI omega t minus C y. Okay, so this is a compact way to write it. We have, again, let's write it here for clarity. Square root omega divided by 2 nu. Okay, so to find the power dissipated per unit volume, we have to take this expression, plug it into here. And but first, so let's find partial u, partial y. So we have to differentiate this expression with respect of y. So that can be left as an exercise. And so we find, if we expand it out, minus u bar divided by 2 c 1 plus I e I omega t e minus c 1 plus iy, and then minus u bar 2c 1 minus I e minus I omega t, and then times e minus c 1 minus iy. And we note that this is a real number as we want, because we are summing two complex numbers. They are complex conjugate to each other. Excellent. So now what we want to find actually d. So d is as follows. So we average over the period t, so we average in time, but also integrating over the volume. So this is a volume integral of phi, and so that's dv dt. So if you remember here, the dissipation was per unit volume. So it makes sense to integrate over the volume, and we find this is equal to 1 over t integral from 0 to t of the integral from 0 to infinity, and I explain, of partial u partial y squared, and that's a dy dt. So this 0 to infinity is the integral over the whole normal coordinate, but we have to multiply by the area AS. So this infinity makes sense because if you remember at the beginning, I said that control volume extends all the way to infinity. So if we take this expression for the gradient of partial u partial y and we substitute inside here, because we know the expression now, we obtain the following. We get d equal to mu u bar squared c squared as times the integral from 0 to infinity of e minus 2cy in dy. So this is the power dissipated into heat. And of course, this depends on the dynamic viscosity, because the dissipation into heat occurs because of viscous effects. Very good. And the units of this is watts. So C is square root of mu divided by 2 nu. And of course we can do this integral easily. We integrate and we get d equal mu u bar squared c squared as, which is the surface area, minus 1 divided by 2c times e minus 2cy, integrated from 0 to infinity. And you see here that's what's left of d is actually only the decaying exponential, and all the terms we have found before that depended on time cancel out because we integrating over time. So you can try that yourself. So all you have to do a bit of algebra, and the final expression is d equal u bar squared as divided by 2 and then square root of mu times rho pi divided by t. So now I have substituted the expression for omega equal to pi t. So we have obtained the power dissipating into heat because of viscous effects. Okay, what we can do, we can check the units. That's always important. So if you check the units, then you find then this is the units of D, and nothing but kilograms times meter squared divided by s cubed, and this is watts. Okay, excellent. So what's the final step of our analysis? Well, we can check in a different way because we know that the P spent is equal to D, and we can find now P spent directly and see if we obtain the same expression as the dissipation. And again, if you look up in Hinze, you also see how to compute in turbulence. So how to compute the power spent by viscous effects. So in our case, if we average this power over time, we have the integral from 0 to t of u at the wall, so y equals 0 as a function of time, times a partial u partial y at y equals 0 times the area, the surface area, and then we integrating over time. Of course, this is the power spent at the wall, so we have a velocity times a force. So the force is nothing but the shear stress, so mu partial u partial y multiplied by the area. And so of course here there's no integral along the wall normal direction. So again, if we substitute the expression for u at the wall and the partial u partial y, setting y equals 0, then you get something like, well, exactly, not something like, exactly, as mu as u bar squared times c divided by 4, and then the following, e I to omega t plus 2 plus 1 minus I e minus 2I omega t, and this is averaged over time. So, but these two terms vanish because over a period, this is two periodic function in the period. So if we integrate, they cancel out. So we obtain P spent equal to mu times as u bar squared divided by 2 square root of mu divided by 2 nu, the kinematic viscosity. And we rewrite this as u bar squared AS divided by 2 times mu pi rho divided by T. And so exactly the same expression as the dissipation into heat that we found before. So this is a great check. Great check. Okay, that's it for today. Thanks for watching, and I'll see you in the next video. Bye.